So today we're going to talk about the direct comparison and the limit comparison tests to test whether a series is converging or diverging. All right. Sometimes the direct comparison test is also called the comparison test. Okay. And so what we've had so far is we've had the nth term test, we've had the p-series test, we have the integral test, and the geometric series test. All these tests to see if a series is converging or diverging. All right. Well, what if we don't have one of those specific ones that allows us to use those tests? What else can we do? All right. So for instance, if we see this, right, 1 over 2 to the n, we should recognize, okay, that's really 1 over 2 raised to the n, because I could do raise the whole fraction 1 over 2 to the n power. That's a geometric series, right? And we know that that's going to converge, right? But this one's not a geometric series, okay? And this would be hard to integrate for the integral test and just a lot of other things. This was very difficult to do. So we have to come up with some other test. This is the p-series, right? Because n to the power of 3, right? But this one's not a p-series, okay? So we got to come up with a way to do these ones that are slightly different. And how do we deal with it? This one right here this one's easy to integrate, but then this one's not easy to integrate, okay? All right, so and the only difference is this one's being squared. This one we'd have to do a u substitution where u would be n squared plus 3, and then we'd have to compensate and make this become 2n, but we can do that, right, for the integral test. All right. So the next two tests are going to help us determine the convergence or divergence of these ones that are kind of like a geometric or kind of like a p-series or kind of like the integrals one. All right. So that's what we're going to learn next is these next two tests. Okay. The direct comparison and the limit comparison tests. Okay. So the direct comparison is we need to find, we want to let a sub n, those are the terms of the series, right, be less than or equal to some other terms of the series for all n values, okay? So basically, if we were to graph it, this series right here, the terms of the series would always be above this series, okay? So what happens is if this one is converging, okay? So if the bigger one's converging, then that means that this one is always going to be lower. So it also has to converge, okay? So one that's bigger, if this one's converging, it's squeezing this one down and so that they both converge. All right. So that's what this says. If the bigger one converges, then the smaller one must converge. Okay. Now, if the smaller one diverges, that's going to push the bigger one out. Okay. So this b sub n or the a sub n, depending on whether we want to check for convergence or divergence, if we want to show that something's converging, we want to pick a series that's converging, and this is the one we're going to use, and we're going to compare it to this one, and then we'll know this one is, okay? So this one's going to be for converging. This one's going to be like a p-series or geometric series or one of those that's easy to find. And then because this one's always going to be smaller than this one, we'll be able to do it, all right? Now, on the other hand, if we're trying to show that this one diverges, and if we know the smaller one diverges, right? So this is going to be the one that's the p-series. If we're trying to show divergence, we're going to show that this p-series diverges or this geometric series diverges. And then therefore, since this one's smaller than this one also has to diverge, okay? So informally, I say this, okay? If the larger series converges, this helps me understand what's going on here. If the larger series converges, the smaller series must also converge, because this larger one is squeezing this one down, okay? And if the smaller series diverges, the larger series must also diverge, okay? All right, because this one, the smaller one, it's diverging, so it's pushing this one away from anything that it could converge to, okay? All right, so that's kind of how I picture it in my mind, if that helps you out, all right? Okay, so let's actually do some problems now. So here's what we want to do. We want to determine the convergence or divergence of sigma n equals 1 to infinity of 1 over 2 plus 3 to the n. So the key here is like the 1 over 3 to the n. This is really kind of insignificant, okay? So what we're going to look at is 1 over 3 to the n, and we're going to compare it to that. Now, why am I choosing that one? Because I know that that one's going to be a geometric series, okay? So let's take a look at this. So sigma n equals 1 to infinity of 1 over 3 to the n power. That can be rewritten as sigma n equals 1 to infinity of 1 over 3 to the n power. And what we should realize is that's a geometric series now, right? So anytime we have this, that's a geometric 1 over 3 to the n power. We know that that's going to be a geometric series, okay? So we have this, and we know that sigma n equals 1 to infinity of 1 over 3 to the n converges. Now, how do I know it's going to converge? It's because r equals 1/3, and this r value is between -1 and 1. So r is between -1 and 1, and we'd say by the geometric series test. Okay, so how does this one right here compare to this one? Well, this one's going to be smaller, okay? So 1 over 2 plus 3 to the n. This is my nth term, right? 1 over 2 plus 3 to the n. That one's going to be smaller than this one. So less than or equal to 1 over 3 to the n. Now, how do I know? You may be wondering, like, how do I know that this one's smaller? Okay, so if you compare these two, right, this one's going to have a bigger denominator because we're adding 2 to the 3 to the n power. So this one's always going to be slightly smaller than this one because we're always going to add 2 to our denominator here, which actually makes the overall fraction be smaller. Okay, so that's how I know this one's going to be always going to be smaller than this one. Okay, so what do we have here? Well, we have a bigger series, right? A larger series that we know converges. Well, that means this one is also going to have to converge, and it's by the geometric series test, okay? So we'd say, therefore, okay, sigma n equals 1 to infinity of 1 over 2 plus 3 to the n converges by the direct comparison test. Direct comparison test. Okay. All right. So you got to establish, okay, so that one of these is either converging. You got to pick something that looks like a geometric series or probably a P series, okay, and show that it's either convergent or divergent. And depending on whether it's convergent or divergent, you need to show that the one that we're trying to find is if it's convergent, we need to show that this one is smaller than this one, okay? Or if it's diverging, we would need to have this one diverging, and then we'd be using this one to determine the convergence or divergence of this larger one, okay? So if the smaller one is diverging, then the bigger one's diverging, okay? All right, let's do one more. So on this next problem, we want to determine the convergence or divergence of sigma n equals 1 to infinity of 1 over 2 plus the square root of n, all right? So this kind of looks like a P series, right? Because this is into the 1/2 power. So what if we try, and let's see what happens if we try to compare this series to this series. So let's take a look at sigma n equals 1 to infinity of 1 over the square root of n, which is really into the 1/2 power, okay? So what do we know about this? Well, P is equal to 1/2. And since 0 is less than P, less than or equal to 1, we know that this series is going to diverge, right? So sigma n equals 1 to infinity of 1 over n to the 1/2 diverges by the P series test. Okay. Now, what we have to show, if this diverges, we have to show that this one is actually smaller than this one, right? Okay. But is that the case? Now they're both square roots of n, right? But this one's 2 more. This denominator is 2 more. So that actually makes this one become smaller than this one because the plus 2. So really what we have is 1 over 2 plus the square root of n. That one is going to have to be less than or equal to 1 over the square root of n, or n to the 1/2 power. Okay, so what does that mean? Okay, so this one's diverging, but to know about this one would have to be bigger than this one, right? So that what this means is we can't use the direct comparison using this series compared to this one, okay? Because remember, if we can show that the larger series converges, the smaller one converges. And if we can show that the smaller one diverges, then the bigger one diverges. So here's the problem. We have the bigger one, and if we want to use this one, it would have to be converging, and then we could say this one converges, right? So what else could we use on this? Okay. So we can still, let me write this. You can't use the direct comparison test. Right? So you can't use it. Not using this series, okay? So what else could we use? Okay, so we probably still want to use a power series, okay? So what if we take a look at something that where the denominator is going to be bigger than this denominator, right? Okay, so in that case, because if we can show the denominator is bigger than this one, then that means the fraction is going to be smaller, right? Okay, so something that's going to eventually be bigger is this. Okay, so sigma n equals 1 to infinity of 1 over n. Okay, so that's a power of 1. So you can think of like, how do the graphs of the square root of n and n compare? Okay, so the square root of n, all right, grows really fast at the beginning, but then slows off, right? That's basically I'm asking you to like think about the square root function. Okay, what does the graph look like? Right at first, it grows really fast, right? But then it kind of tapers off and doesn't grow as fast as your n. In this case, n gets bigger and bigger and bigger. Okay, so for this one, this is going to be a good comparison. I'll show you why. Okay, I'll talk more about why this one's a better one. Okay, so p equals 1. And since p is less than or equal to 1, okay, or between 0 and 1, okay, then we know that this series n equals 1 to infinity of 1 over n diverges by the p series test. Okay. Now, what we have to show, since this one diverging, we have to show that this fraction 1 over n is actually smaller than this one. Okay, so I want to show you. Okay, so I've typed in, for one of my sequences, I've typed in 1 over n, and I've typed in 1 over 2 plus the square root of n. Okay, so the blue one's going to be 1 over n. That's the one we're using, right? We know that this one diverges. Okay, and if we can show that this one is smaller than this one, then we're going to be able to say that, okay, this one diverges. Okay, so if I press graph, this is what it looks like. Okay, so once again, the blue one, okay, is my 1 over n. Now at first, right, the other one is smaller, right? But then all of a sudden, the blue one here, after a while, after n equals 4, right? So 1, 2, 3, 4, right here, they're the same right here. You're not seeing it, but the red dot, and let me zoom in even on this. Okay, so right here, this point right here, that's the same point on both graphs. Okay, so all of a sudden, after n equals 4, then what's happening is the 1 over n is smaller, and we know that this one's diverging, and because this one's diverging, this one's also diverging. Has to. Okay, all right, so let me zoom back out so we can see this, okay? So what we just established by looking at that graph is that 1 over n is less than or equal to 1 over 2 plus the square root of n. Now, this wasn't always true. It was only true when n was greater than or equal to 4, okay? So we know this one diverges. We know that the smaller one is the one that's doing the diverging, okay? And so we know that this one is going to also diverge. So we'd say sigma n equals 1 to infinity of 1 over 2 plus the square root of n diverges by the direct comparison test. And what you're noticing here is this is the difficulty in the direct comparison test, is like picking another series, okay, that will do what we want it to do, right? So this is by the direct comparison test. Sorry, can't spell. All right. So that's what we do. Okay, so once again, let's why is this one? I mean, yes, the graph showed it, right? But you got to realize, okay, that the square root of n grows really fast, but at some point, n grows faster. And since n is growing faster than the square root of n, this 2 is insignificant, really, okay? But since this is growing faster, this is going to cause the fraction to be smaller than this fraction at some point, okay? And that point is n is greater than or equal to 4. All right? Okay, so let's look at the next test, which is called the limit comparison test. Okay, and I think that one's going to be a little bit easier. This one's very, very difficult. I think of all of the series tests for convergence, this is probably the direct comparison test is probably the one that I use least because of this fact. Like, it's hard to pick one that's doing what I want and smaller or bigger, depending if it's divergent or convergent. Okay. All right, so let's look at another problem, or let's look at the limit comparison test rather. So we're going to use this a lot of times. We'll probably use this more than that direct comparison test, okay? But often, I'm just going to read this. Often a given series closely resembles a p-series or a geometric series. Yet we can't establish that term-by-term comparison. And that's like what we had difficulty with just in the last problem, okay? Necessary to apply the direct comparison test. So then under these circumstances, okay, you may be able to use this other comparison test, and it's called the limit comparison test, okay? So we don't have to, we have to pick another one to compare it to, but, all right, it's a little bit easier to pick, and we don't have to show that one is smaller than the other or one is bigger than the other, okay? So we have to do this. The terms of the series is greater than 0 for both of them. And then we're gonna take a look at what's the limit as n approaches infinity of the nth term of one of the series over the nth term of the other series, okay? And if this limit comes out, and this is what's important, is it's finite and positive, okay? So it has to be positive and it has to be a number value, okay? It can't be like infinity or something like that, okay? Then what happens is they both do the same thing. So if this limit comes out to be finite and positive, then the two series either both converge or both diverge. So we got to know what one of them's doing. Like, is one of them converging or is one of them diverging? Okay. So we need to know that, all right, that we need to know whether it converges or diverges to use this. Now, a lot of times, yeah, it's going to be like a P series that's really quick to say, hey, this is converging, or hey, this is diverging, or a geometric series. So we want to use something that's really quick and easy to compare it to, okay? So another thing, the limit comparison test works well for comparing a messy algebraic series with a P series and choosing the appropriate P series. Okay, so we're going to have to look at what's the magnitude, okay, of the nth term, okay? So like this one, okay, 1 over 3n squared, we would compare that to 1 over n squared. And so since our p-value is 2, right, and when it's bigger than 1, we know it converges. We know since this one converges, and if we try to do the limit, all right, then that's going to show that both these converge, okay? This is into the 1/2, okay? So when we do the limit, all right, or this 1 over the square root of n, this is the one we would compare this one to this one, okay? So we don't even have to kind of worry about the 3 even. It's the square root of n is what we have to worry about. So this one we have to worry about n squared, And the bottom, we have to worry about n to the fifth. So that's why we're only looking at those powers, okay? That's what's really causing the growth. And then that reduces to 1 over n cubed. So that's, we want to compare this one to 1 over n cubed. Now, what would we know? We know that this one converges by the p-series test. And we know this one diverges by the p-series test. And we know this one converges. See, that's what I mean. Like, we have to know the convergence or divergence of one of them and then compare it to the other one. And we want to use the magnitude of it. So that's why we got to worry about the nth term magnitude. So this would be n squared over n to the fifth. Okay. All right, let's do a problem now. Okay, so when n equals 1, this is going to be greater than 0, right? Okay, when n is 2, n is 3. So all these terms are going to be greater than 0. Okay, what do we want to compare this to? Well, this 3 is really insignificant. So it's going to be 1 over n that I want to compare this to. So sigma n equals 1 to infinity of 1 over n. Now, we know that the power here is 1, so it's a p series. This is also called a harmonic series, right? And since p is 1, that means it's going to diverge, okay? Another, and I said this when we talked about the p-series test, you can say for this particular one, you can say this is a harmonic series. So you could give this for justification too. Is a harmonic series, or is, I should say, not there's only one of them, is the harmonic series, and therefore diverges. Okay, so we're going to compare these two, right? And we're going to do this limit comparison. So we're going to take the limit as n goes to infinity of, this is my a sub n, so 1 over 3 n plus 5 over 1 over n. Okay, so this is going to happen a lot where we have a fraction over another fraction. This is really dividing two fractions. So this becomes the limit as n approaches infinity of 1 over 3n plus 5 times n over 1. So you can switch this to multiplying by the reciprocal of this denominator, okay? All right, so that makes this the limit as n approaches infinity of n over 3n plus 5. We can evaluate this limit using magnitude, right? So this is the limit as n approaches infinity of n over 3n. Well, that would turn out to be 1/3. Okay, so we know that this is 1/3. So we know that the limit exists, right? It's finite and it's also positive, okay? And then we know that this one diverges, right? So what does that mean? That means this one also diverges. So we can say sigma n equals 1 to infinity of 1 over 3n plus 5 diverges by the limit comparison test. So that's how you use this limit comparison test. Okay, is you gotta find the limit. You gotta pick one that you know the convergence or divergence of, and then find the limit. Okay, and I always this is the one I'm trying to figure out. Okay, so that's my a sub n, and this is my b sub n. Okay, and then work out that limit, show that it comes out to be finite and positive, and then we know that they're going to behave the same exact way. So this one diverges, so this one also diverges. Okay. All right, so let's take a look at the next one. Okay, so we want to, again, determine the convergence of this. Okay, so we got to look at the square root of n over n squared. That's what we're gonna have to look at for this. Okay, so I'm gonna look at sigma n equals 1 to infinity, the square root of n over n squared. Okay, so that becomes sigma n equals 1 to infinity of n to the 1/2 power over n squared. Okay. And so we would do 1/2 minus 4/2, which is -3/2, right? So the power is -3/2. So that'd be n equals 1 to infinity of 1 over n to the 3/2 power. And this is a p series, right? Because we have a power of 3/2, right? And so what do we know? P is equal to 3/2. All right. And since 0 is less than P, less than or equal to, sorry, whoa. I'm writing the wrong thing. Hold on. I'm writing the wrong thing. So this P, since P is greater than 1, right? We know that this series right here, which is equivalent to this one, converges by the P series test. So we know this series, n equals 1 to infinity of the square root of n over n squared, converges by the P series test. All right. So back to this one. Now I'm going to write these out as exponents, okay? So we want to find the limit as n approaches infinity of n to the 1/2 over n squared plus 1. And we're going to compare that to this 1 over n to the 3/2. Okay, so this is a fraction right here, and this is a fraction right here. So this is equivalent to the limit as n approaches infinity of n to the 1/2 over n squared plus 1 times n to the 3/2 over 1. So that's equivalent to the limit as n approaches infinity of n to the, this would be 4/2 or n squared over n squared plus 1. And so we just look at this, n squared over n squared, right? That's what's causing the growth. So this would be the limit as n approaches infinity of n squared over n squared, which is 1. And so that's positive and finite. So they're going to be doing the same thing. So since this one, we established by the P series that it converges, we also know that this one's going to converge because this limit came out to be finite and positive. Okay. So we now know that the sigma n equals 1 to infinity of the square root of n over n squared plus 1 converges by, and what did we use to establish this? We used the limit comparison test. Okay. All right. So let's take a look at a problem, then another problem. Let's try to figure out like, how could we do this? Okay. All right. Another problem that we're not going to necessarily use limit comparison. Let's take a look and see what we could use to figure it out. Okay. So for this one, we want to determine the convergence or divergence of this. So we have an exponential multiplied by n, right? 2 to the n times n. And then we have an n cubed in the denominator. That's really what's causing the growth. So it's a combination of these two together, okay? So I want to, what do I want to compare this to? Well, I can ignore the 4 and ignore the 1, and I'm going to look at n over 2 to the n over n cubed. Now that's going to be helpful because my n's are going to cancel here if I simplify it and disregard the 1 and the 4, okay? So here we go. So sigma n equals 1 to infinity of, we want to look at n to times 2 to the n power over n cubed. Okay, so this n, because I'm disregarding the 4 and the 1, those are really insignificant in terms of magnitude. All right, what I want to do is simplify this. So this becomes sigma n equals 1 to infinity of 2 to the n over n squared. All right. Now, this is the hard part. Okay. So how do you pick one to, how do we figure out the convergence? Because this isn't a geometric series and it's not a P series, right? And I definitely wouldn't want to integrate this. It's not easy to integrate. So like, I wouldn't want to integrate this. So forget the integral test, right? So what else do we have? All right. And so you should be thinking, okay, so what are some other tests that we can use? Can't use a P series, can't use geometric series because it's not a geometric series. You can't, I wouldn't use the integral test because it's just too hard to integrate. So we learned something at the very beginning. And if we take a look at the limit as n goes to infinity, If it doesn't come out to be 0, then we actually know it diverges, right? So this is a really quick way of showing that something diverges, okay? So we haven't used this in a while, okay, but we could take a look at this, the limit as n approaches infinity. Because one thing I'm noticing is that this is going to grow way faster than this one, right? And because that's going to happen, that means this is going to take off and it's going to be infinity, okay? So what this means is limit as n approaches infinity. We would need to write this of 2 to the n over n squared is equal to infinity, all right? And because it's not equal to 0, that automatically means that this series diverges, right? Now, if it equals 0, that doesn't mean it converges, okay? But if it doesn't equal 0, it definitely does not, it definitely diverges, okay? So we'd say since the limit as n approaches infinity of 2 to the n over n squared does not equal 0, we know that this series n equals 1 to infinity of 2 to the n over n squared diverges by the nth term test. Okay, so we know this one diverges. So if we can do the limit and show that it's finite and positive, then we know that this series is going to come out and diverge also, okay? So we got to do this limit. Okay, so the limit as n approaches infinity, okay, of this is my a sub n, okay? So n times 2 to the n over 4n cubed plus 1, and I'm going to compare that to 2 to the n over n squared. Okay, so this becomes this becomes the limit as n approaches infinity, and it's going to be this fraction. Okay, so n times 2 to the n over 4n cubed plus 1 times n squared over 2 to the n power, right? And if you look, okay, my 2 to the n's are going to cancel here, right? So I'm going to be left with the limit as n approaches infinity of n times n squared, which would be n cubed, over 4n cubed plus 1. So to do this limit, we just need to compare this to this, right? So this would be the limit as n approaches infinity of n cubed over 4n cubed. And this would come out to be 1/4. So it's finite and positive. So what does that mean? That means these are doing the same thing, right? So if this one's diverging, then the original series is also diverging, okay? So we know that sigma n equals 1 to infinity of n times 2 to the n over 4n cubed plus 1 diverges by the limit comparison test. Okay, and that's how you do these. That's how you use the limit comparison test and the direct comparison test. And I definitely think the limit comparison test is a much easier one to use than the direct comparison test. Okay, a lot of times that one's an easier one to use. I'll tell you that. Okay. All right, that's it. That's how you do direct comparison test and limit comparison test. All right, so go do your homework, and I will see you later.